since this is so small, it's insignificant. Yeah. And so let's look at some of the early lasers. Let's go back to our recording. So the ruby sapphire laser, ruby is a sapphire crystal doped, which is an aluminum oxide crystal, and then it's doped with chromium. So ruby, you're looking at the chromium, the absorption spectrum of chromium when you see that red color. Okay, and so if it absorbs red, it can emit in the red as well. So it produces a red laser, and it has again a very intense pump. You can pump that chromium up, and you see actually the term symbols up there. We have a quartet F2 and a quartet F1. Both of those absorb, so you blast it with visible light, and you can actually get the chromium atoms to be in a population inversion with the ground state. So it's efficient enough that you can deplete the ground state and create a population inversion, and then you get the lasing action. This is interesting because you're pumping it in the visible and you're getting visible light out. So 694.3 nanometers was the laser. The neodymium YAG laser is very, very common. That's that 1064 nanometers or 1.06 micron line right here. And these are the neodymium atoms energy levels. And then you hear about helium neon lasers. This is an interesting system because the helium absorbs the light and it bumps into a neon atom and excites it. And so this is a strange thing. You're absorbing with the helium gas, and then the collisional transfer of energy from the helium excites the neon, and then the neon is the laser. So that's totally bizarre. And they get a population inversion because the neon is excited up here, and it's one of those intermediate states that it's lasing to. So it doesn't have to compete with the ground state. You get a population inversion with one of those intermediate states. Here's the laser selection guide. So you can find these. This is on Wikipedia. So you look up laser on Wikipedia, and you see all of the different types of lasers. Now, what types of lasers have you heard of? Yeah, laser pointers like these. These are like diode lasers, but you might have heard of a helium neon laser, so we've talked about that one. These diode lasers are just light-emitting diodes, and they cover the whole range. But have you heard of a CO2 laser, like these laser cutters?
I think I've heard of them.
Yeah, so here's a CO2 laser. It's that CO2 line in the mid-infrared. And so that's the line that you won't be able to see that beam, which makes it really dangerous. It's a powerful laser, and it's in the infrared. So you won't know, you won't see it, and it can burn you. Okay. We had a laser beam going between two laser tables in our research, and that was a bad idea. We should have had something to block it off. And a guy walked between the tables, and it was a pulse laser, I told you, right? So it popped him 3 times through his shirt. It was in the infrared, and he pulled his shirt up. It looked like cigarette burns, like it blistered up immediately. Yeah. He walked through and he was like, yeah. We're like, oh, don't walk through there. And he looks, he's like, man, you got me. Totally bad. I'm admitting this on camera. But anyway, so laser safety is a big deal, and it's too late, when you get hit. So that's the CO2 laser. If you wanted to help the field of research, we need more tunable lasers in the mid-infrared to do trace analysis. So like you could get in there and analyze for carbon monoxide. You saw those really narrow lines. If you wanted to do research on something that small, you could tune that with a laser. If you could get these lasers to tune, one way to change the dimensions of the diode, but that only gets you a few wave numbers. A lot of times they'll use dyes, and they'll use a grating inside the lasing cavity, and they'll change the resonant frequency of the cavity, and they can tune the wavelengths by putting a grating inside the lasing cavity. So that's another way to get tunable lasers. Exciplex lasers. This was in the homework. One of the coolest ways to get in population inversion is for the ground state not to exist. Okay. So how can you get a molecule not to exist in the ground state and only exist in the excited state? You play around with bond order, right? If you have an excited molecule where the electron is up in, say, an excited state but a bonding orbital, then it can be a molecule in the excited state, but when that electron drops down into an antibonding orbital, the ground state is not bound, or it's very weakly bound. And so then there's no ground state, there's only an excited state. So that's how we use, those are chemical lasers, or Exciplex lasers, or Eximer lasers. And these are very powerful lasers, especially in the UV. It's one of the first ways to get a UV laser. And this is the laser that was used in LASIK surgery when my wife had LASIK surgery. And so it was an argon fluorine Eximer laser. And again, it was UV, so you couldn't see the beam, but you could see when it hit something. And so I was all excited. I was in the control room, and here she's got her, cornea held open, and it's been cut and flopped over, and it's blasting away at the cornea. And I'm like, wow, this is great. You could see the blue flashes of the light as it was just evaporating the cells inside her cornea. Yeah, and it was just changing the contour of her lens. Then they flopped the thing back over, put a protective contact lens on it, and corrected her vision. It was super awesome. But the laser was the bed that she was lying on. So she was laying on the laser device, and then the optics went up and down and then shot her in the eye. Yeah. And so, and it was cool too, because he put 4 dots like with a Sharpie, or a medical Sharpie. Probably still just a Sharpie with extra. and so then the computer locked onto those 4 dots, and her eyes moving around. I could see both visions. Like over here, her eyes moving around like this. And over here, her eyes perfectly still. Because over here, the computer's following it around. And I said, wow, how fast can the computer keep up? And he says, the computer can move around in like 0.1 millisecond. And your eye moves around between 5 and 10 milliseconds. So it has it's like 10 to 100 times faster than your eye. He said, it can't keep up with a sneeze. So we tell him, if you're going to sneeze, tell me, and you'll stop the laser, you sneeze, and then you get back in position. But her eyes moving around on this screen, and it's solid there, and the laser's doing this. And there was a crosshatched area, and I said, what's that? And he said, that's where the laser is not supposed to shoot, because that's the flap. So this scalpel cut the cornea and flapped it over, and that's the hinge. And you don't want to cut the hinge, right? And so then he ablates the lens, and then hinges the top of the cornea back on top, and then they've got it all figured out. If this is grossing you out, I see some people are like, no. But that was an Eximer laser, an excited state laser. So here's the potential energy surface for an Eximer laser. Isn't that cool? So here we have the fluorine atom coming in. It's excited, the 3s, excited compared to the molecule. And it has an electron in a non-bonding orbital, so the 3s on the fluorine. And that forms something that has a bond order. It looks like from this, if we take the lower areas as canceling each other out. So we've got a bond order of 1. And then when that electron relaxes, we've got a bond order of 1/2. And that's really not enough for this molecule to hold together. And so there are no molecules in the ground state. There are only excited state molecules. And so you naturally have a population inversion. And the thing that limits this is just how fast you can mix those gases. And so you just take fluorine and argon, blast them together, and then you put that in the resonant cavity, and you get emission, and you get a laser. So it's a very fast laser, puts out a lot of power, and so they're also using this for weapons too. So this is a laser on a 747, and it can shoot down missiles. So this is part of the laser or missile defense system that we have in our country. Here's one that's on a C-130 cargo plane. And if you click that link, we don't have time to watch all the videos, but if you go back online and pull this PowerPoint down and play it and click that link, you'll see this laser is burning a car hood, just to show you how accurate it is. It's like a 1 foot square on a car hood, and it's just burning a hole in the hood. We can shoot through a missile, it can shoot through the plane fuselage. There's lots of things that our missile defense agencies doing with Exciplex lasers or chemical lasers. You can also do spectroscopy. You can send this out to correct for the atmospheric aberrations, and so we can get images from Earth from our ground-based telescopes using lasers to correct for the atmospheric disturbances that are better than the Hubble telescope. So we put the Hubble telescope up, and it got some great images, and then we learned how to correct for atmospheric disturbances with lasers, and now we can get really good ground-based images using what they call a guide star laser. So anyway, pretty neat. So that's it for the lasers. Let's take a Kahoot and practice.